This project involves real surgery and human tissue images, all of which have been pixelated or processed in grayscale. This project is an iteration of Ideation 1, focusing on emergency medical transport in urban settings. Target audience: surgeons preparing for operations and kidney transplant patients. Establish drone docking stations at key medical and transport hubs to shorten organ transport time and preserve their viability. Organ transplantation saves lives and offers hope to countless patients. Kidney transplants are especially common due to the high incidence of kidney disease, the burden of lifelong dialysis, and the fact that humans have two kidneys, allowing for donation. Organ transplantation is a critical step in saving lives. However, uncontrollable factors can cause organ degradation, preventing patients from receiving treatment. Every extra second outside the body reduces an organ's viability. Longer transport times increase post-transplant rejection risks. Kidneys have high ischemia resistance, making it easier to transport. Advanced surgical techniques and anti-rejection treatments improve transplant success rates. This project focuses on kidney transport as the research subject. Efficient transport is critical but faces many challenges. Delays and unstable temperatures reduce organ viability and transplant success rates. High transport costs are not covered by insurance, placing a financial burden on patients. Even when patients pay high fees, issues remain. Among 8,800 transported organs, 370 were delayed and 170 were lost. Transport problems contribute to 30.4% of transplant failures. With climate change leading to increased extreme weather, the situation worsens. Transporting an organ requires a team of specialists, increasing costs and time. 15% of transport errors are due to cold chain failures, further reducing survival rates. This page is current transport methods and their limitations. The first one is helicopters, fastest but most expensive, with landing restrictions. The second one is ambulance, more affordable but highly affected by traffic, leading to delays. The third one is air transport combined with ground logistics, not considered in this project. Money becomes the deciding factor in saving a life, which is unfair. Not all families can afford $20,000 for organ transport. Is there a better alternative? Enter into drones. With technological advancements, drones can transport medical supplies quickly and efficiently, flying over congested traffic with minimal energy consumption. I did research. Three medical experts believe drone organ transport is feasible and promising. One of them successfully transported a kidney using a drone. I did business research. China leads in drone innovation, particularly DJI's Flychart 30, which carries 30 kg, has a 16-kilometer range, and is resistant to environmental conditions. This proves that drone-based organ transport is technically possible. Through market research, we identified two types of transport drones. One is containerized drones, another one is hunting parcel drones. Containerized drones are better suited for transporting organs, as they require shock resistance, stable environmental control, and secure handling. From my reflective paper, 5 key factors emerged: safety and public perception, transport efficiency, organ blood stability, policy and regulations, technology and innovation. For drone to operate in cities, several issues must be addressed: noise levels, local drone regulations, public privacy concerns, and public perception and safety assurance. Our drone will be larger in size. The significant name is PAV, and here is some research I've conducted. To understand public opinion, I interviewed 3 residents from urban, suburban, and rural areas. They all agreed that drones are acceptable if they improve healthcare efficiency and safety, but there is also some concerns: reliability, noise, and government regulations. I made a design simplification. Organ storage box is the most important part. Temperature control is key to organ survival. I researched 4 existing storage methods, but the most commonly used is iceboxes. Well, iceboxes are affordable and convenient. They cause irreversible organ damage. To avoid similar flaws, I explored alternative solutions. I noticed a new preservation technology, pneumocymatic machine perfusion. This method mimics the human body's environment, preserving organs for longer. My research identified it as the most effective low-damage solution. Certainly, there is no commercialized perfusion system for kidneys. However, its function is similar to dialysis, which supports metabolism outside the body. I researched the principles of renal dialysis. I interviewed Dr. Ren, who confirmed that dialysis acts like a blood filtration system for kidney patients. At the same time, a European patient with 10 years of dialysis experience shared her struggles. She has waited years for a suitable kidney and spent large sums on organ transport. She strongly believes my project would benefit patients. I studied the NCU-18 dialysis machine, analyzing its structure and function. I disassembled the real instrument, and I thoroughly understood the working of this machine, its inner workings. I interviewed an engineer of renal dialysis prior to choose whether it is possible to change some structures to achieve the purpose of transforming the renal dialysis machine into an organ extracorporeal blood circulation system, and I got the technical yes. Modifying 6 structural components could turn a dialysis machine into an external organ perfusion system. This proved the feasibility of my technology. I analyzed London hospitals performing organ transplants and found they are mainly located in suburban areas, reducing urban public concerns. Further research in downtown London showed that most buildings are 100 meters tall, while my drones operate at 400 meters, eliminating risks of collisions or privacy breaches. Here I designed and refined the drone operational workflow. Concept sketches, prototype design, AI-generated appearance models, upgraded structural design, CAD model development timeline and introduce. Here's my structural design idea 1. It was abandoned because it could not be fully automated. This part is structural design idea 2. It's real transport loading without workers. Design of storage box loading method. Run the motor to lower the clips and open them until they line up with the holes in the box. Place the clips into the box. Then reactivate the clips to secure the box and activate the motor to raise the organ storage until into the drone. Here is CAD detail drawings of various locations. Final CAD model. 3D printing process. 3D printing of the final prototype. British Emergency Medical Colors for visual identity. Material selection analysis. Flight mode structure and dimensioning. Landing pattern structure and dimensioning. Organ storage tank structure and dimensioning. Renderings for flight version. Renderings for floor standing version. Renderings for organ storage box. Rendering highlights. X-plot views. Usage scenarios. This is my version of the story, the same process that was used for this project, where the doctor operates on the operating table to remove the organ. They then chemically process them and place them in the storage containers and connect them to the tubes. The medics make sure the cargo is received by the drone. The storage box goes into the internal cargo hold and takes off. Drone in transit. Government bike. Office staff monitor the drone's location and status in real time. Destination doctor waiting for the drone to land. Pulmonary combination lock unlocks the organ transport box. The organ storage box opens. Doctors take it to the operating theater. Automated and automated tools in the health center sector can improve efficiency, reliability, and emergency response speed, but popularity is limited by operational complexity, functional limitations, and user trust issues. Human-centered design can simplify operations, increase adaptability and trust, and enable technologies such as drones to fulfill their potential in emergency response. In the further development, I would finish the app interactive system and the UAV parachute system to make this project more complete and secure. That's all of today's presentation. Thank you for listening.